Question 5 is where it starts to pick up a little bit. So here we've got a question looking at trigonometry, arcs and sectors. So we're told that in this diagram, triangle ABC and sector BDC are as shown. We've got the radius, which is 6, and the points A, B and D are on the same line. We're told that AB is 2 root 3, BC is 6, and the area of triangle ABC is 3 root 3. And critically here, we are told that ABC is obtuse. Now, it's not to scale, but we can see it does appear to be obtuse, but that's important, we'll see in a minute. In part A, then, we are asked to find angle ABC, which we're told here is obtuse. So, looking at the available information in triangle ABC, we can see that we have got a side. The angle is what we're trying to find out, and we've got a side here. So we've got the side angle side, and we've also got the area, which is 3 root 3. So we should recognise that the information we've got here is going to require us to use the area for a triangle using trigonometry. So in the formula booklet, it's going to be half AB sine C, and we know that gives us the area. So C is going to be this angle here, and A and B doesn't actually matter which way they go around either of these lengths here. So let's have a look. Half times A, which I'm going to say is 2 root 3, times B, which is 6, times sine C, and we know what that's going to equal. It's going to equal 3 root 3, because that's the area that they tell us up here. So half times 2 is going to be 1 root 3 times 6, so that's going to be 6 root 3 sine C is equal to 3 root 3. So I can rearrange that to solve for sine C, which is going to equal 3 root 3 over 6 root 3, which is going to give you half. So we therefore need to find the inverse sine of a half. Now, very easy here, after practicing a lot before the exam, to jump in straight away and say inverse sine of half is 30 degrees. However, we are told that ABC is obtuse, so therefore we need to do 180 minus 30, or pi by 3 indeed, pi by 6. So the inverse would be 150 degrees, which we can express in radians as 5 pi by 6. So that is angle ABC. In part B, then, we're asked to find the exact area of the sector BDC, which is this here. So you can see now why in the previous part we actually expressed the answer in radians, because there is a nice simple formula for finding the area of a sector when your angles are in radians. And that formula, again from the booklet, is going to be area equals half r squared theta, where importantly theta is in radians. So let's have a look at this. Half times r squared, well, we know what r is because the radius is here. So that's going to be half times 6 squared. Theta, well, we've just been asked to find this, and we've said this angle here was 5 pi by 6, we expressed in radians. We're also told that point A, B, and D lie on the same line. Therefore, this angle here must be 180, or pi minus this angle here, 5 pi by 6, which is therefore going to give us pi by 6. So we're going to multiply through by pi by 6, and that is going to give us, if we multiply it out, half times pi by 6 is going to be pi over 12 times 6 squared is 36, which will give us 3 pi, but remember this is an area, so that's going to be 3 pi, and we are looking at centimetres squared.